Hello everyone, welcome back. Today we are going to be discussing a few Olympiad inequalities, and I'm going to be starting with the main one of all of them, which is the Cauchy-Schwarz inequality. So let's get into it, and I'll start by picking up a vector a bar, let's say, and I'm writing it in a matrix form. This is a vector of n dimensions, and similarly another vector like this such that ai bi belong to positive integers, natural numbers to be precise. A dot b is equal to the magnitude of them times cos theta. Also, I'm going to be discussing a little bit of a JEE relevant part of the Cauchy-Schwarz inequality, which is going to be super relevant for JEE Advanced 2025. Okay, so the cos theta can be written as a bar dot b bar by the product of the magnitudes of them. Obviously this is less than equal to 1. If I take the other inequality of cos theta being greater than equal to minus 1, well, this won't give me a solution that would be pretty helpful to me. So I'm just going to use this part, and I can write a1 b1 plus a2 b2 till an bn. Obviously I'm taking the dot product of the vectors, and this is going to be less than equal to a1 square plus a2 square an square rooted, and same with the bi. And yes, this is your Cauchy-Schwarz inequality. Pretty simple but very useful. You can also square this, sorry, which is how it is originally known, is this way. Okay, and when you look at it this way, it's pretty obvious, because I mean, taking them separately by squaring all of them and then multiplying them and then squaring, so obviously this is going to be a bigger term. But yeah, this is a very helpful inequality. Now let's try to get a form for JE. So what I would do for this is that I would take, let's say, two functions f of x and g of x, and this would be some f square x and this would be some g square x. So I'm going to be writing something like f of a times g of a plus f of a plus h times g of a plus h till, let's say, let's go on like this till f of b times, one second, f of b times g of b. Let's say I've got this, and then I would have yeah, so, and I would square this, and obviously all these terms would be less than equal to f square a plus f square a plus h plus f, so this would also be till f square b. And similarly I can write this way for g square b. And yeah, so when you take h square on both sides, one h here and one h should be somewhere here, so I can write this as an integral, and writing it as an integral I would have a to b f of x g of x, this integral squared is less than equal to a to b f square x times a to b g squared x. Very useful for JEE. I once encountered a question which actually had this. It was a complex integral, like something like this, and something like this, and you were asked what is the minimum value of these integrals, I1 I2. So this is I1 and this is I2, so what is the minimum value of this? Obviously I can take the roots of this and then square them, so this would be f square x and this would be g square x, and obviously this is greater than equal to these multiply to be 1, as these are reciprocals of each other, so 1 from 0 to 1 dx. So yeah, and this would be squared as well, so yeah, the minimum value is 1 here. Okay, so yeah, pretty useful, and I'm expecting a good question on it, at least something related to it if it's not in the syllabus as well. And also, please make sure to study about the number 2025 before going to the JEE advanced paper. I'm pretty sure there would be a question involving probably like the factors of 2025. I think 2025 is the square of 45. I think, I don't know, probably. Yeah, so 2025 is the square of 45. So yeah, make sure of that as well. These things are pretty, they help in the exam. Okay, whatever. Let's move forward. This is T2's lemma. T2's lemma. Let's try to actually do it the T2 way. Let's put ourselves into T2's shoes and try to prove it. Okay, so what I am given is that this is derived from the Cauchy-Schwarz inequality, and I just want to prove or find I want to find what is the minimum value of this expression. So what is the minimum value of this expression such that ai bi belong to natural numbers? So I want to find the minimum value for it, and for that I would basically just try to let's just compare it with the Cauchy-Schwarz inequality. It was a this this times this, it is greater than equal to the dot product square, right? So what I was gonna do is that obviously this is greater than equal to, so this is on the left hand side. Let's say this is the ai terms, so all the ai terms are congruent to something like ai by root bi. Okay, so I can write this as summation of ai by root bi squared. Now let's form something like, because I want to get rid of these bi, because obviously bi belong to natural numbers and I don't want irrational stuff going into this. So I would try to form a uh, a1 a2 till an here, right? So I would probably multiply by, let's say, bi squared, right? Bi, so root bi squared, and obviously this is greater than equal to ai by root bi times root bi squared. So this cancels out, and yeah, I've got an amazing thing. So clearly a1 squared by b1 plus a2 squared by b2 till an squared by bn is greater than equal to a1 plus a2, sorry, till an square by b1 dividing this here b2 till bn, because this is a positive quantity, so no problem with dividing it. So yeah, this is your T2's lemma. T2's lemma. And once again, I'm just gonna highlight it once. Looks good, I don't know. So this is your, and obviously the most important thing of this video, the Cauchy-Schwarz inequality. Nothing gets better than that. Okay, so yeah, let's now move on to Jensen inequality, and I really like this inequality. Before starting this though, I would say that now that you know the T2's inequality and the basic Cauchy-Schwarz inequality, and if you have studied a little bit of inequalities, please go on and try the Nesbit inequality. It's a little bit similar somehow. If you solved a little bit of inequalities, you should go for it. At least try solving it. I know it's very hard to get it, but yeah, just try to solve it. It's a good problem, and yeah, it's good for your problem solving skills. Okay, so let's jump on to Jensen inequality. Let's take some function like, let's say I have a happy function here, phi of x, and because it's happy, it always keeps increasing, and I'm saying that the double derivative of this, so this is a little bit it's a good function. Also for JEE students, they don't know that this is a good inequality as it proves AM-GM in a very good way. If so I won't be doing that here, but if you want to do, you can apply Jensen's inequality on the function fx is equal to ln x, and yes, you should find fx and e power x, ln x and e power x both would do, to be honest, in this case. One second. Yeah, so fx is equal to ln x mainly is used for AMGM, but I think probably you can do it with e power x as well. Okay, so now that you have this happy function, which is, yeah, so I've taken some function like this, or okay, let's take sad function. I like it more, and I'm saying that it is something like this, concave downward. Okay, so Jensen's inequality only works around the concave function, so I need f double dash x to be greater than 0 or f double dash x to be less than 0. Okay, so I'm gonna be I'll just show it in the f double dash x less than 0 case, and then you can try for the greater than 0 case. It's literally the same thing, just the inequality is reversed. Okay, so let's say this is my sad function, and sad function has, let's say, x1, x2 and x3. So clearly, if I want to locate the centroid, I would have sigma xi by 3 comma sigma sad of xi by 3. This would be the centroid. Okay, now this point, this point, this is not x2, this point is sigma xi by 3 comma sad of sigma xi by 3, right? So clearly, whenever I take these numbers, I can take n numbers. You can say, you can add an x4 as well right here, and the centroid would still lie inside this region. Okay, because this is the basic knowledge, like basic concept of it, right? The basic concept of the centroid, or you can also learn this through, let's say, center of mass. this is this is m2, this is m3, this is m4. Probably this is easier to understand. If you are talking about center of mass, obviously this the center of mass of the system has to lie in this region, right? So let's say I have the center of mass right here, and obviously when I'm taking, so I had this and this. Now my centroid is somewhere here. So when I take the function is always above this part, right? The y component of this and this is easily comparable. It's always going to be more than that. So I can say that sad of sigma xi by 3 is greater than equal to, because yeah, it can be equal as well if the points are pretty close to it, you know, and this is always greater than equal to sigma of sad of xi by 3, and this is for what? Sad of x less than double dash x less than 0. This is true for this. Now you can just use ln x, you know, ln x, you will have f dash x to be f double dash x to be minus 1 by x square, and this is greater than, sorry, less than equal to less than 0. So yeah, you can apply this, and you can find you can just use this ln x, so you can add them up, ln x1 plus ln x2 plus ln x3 by 3. So this would be ln x1 x2 x3, and this is 1 by 3, so I can just take 1 by 3 right here. And here you would have ln of x1 plus x2 plus x3 by 3, and this is greater than equal to, so I just proved AMGM through this, so never mind, you don't need to find that. So you're just left with the AMGM inequality. Yeah, so to generalize this, I can write this as, let's say f double dash x is less than 0. So I can say that f of sigma xi by n is greater than equal to sigma of f of xi by n. Now you can try the case for f double dash x greater than 0, and yeah, comment and tell me if what the result for this would be comparing this and this. Okay, thanks for watching. I'll be back with probably Olympiad content.